Hello, for today's video lecture, we're going to be talking about the centroids of volumes and the center of mass via composite parts. So we're going to start with the centroid of a volume. So the centroid calculation for a volume is going to follow much the same process that we did for areas in the last section, except we're going to use volumes in place of the areas. And then we're also going to be looking at coordinates in 3 dimensions. So volumes, we've got x, y, and z coordinates for our centroids. So putting this all into our process, we identify an origin point and axes, and then we break our volume down into shapes that we can look up on our centroid tables. For this, we're going to be using the 3D centroid tables from the 2D ones we were using for areas. We do need to remember to take into account the orientation and placement of the different pieces. So things may not be oriented the same way in the table as they are in your problem. You'll need to do a little bit of reorienting the pieces to make things work. And also remember that cutouts are represented by negative, rather than negative areas, it's negative volumes here. So if you have a cylindrical cutout, like you drill something out, you can use a negative volume to indicate that cutout. So with this, say we've got some simple shape, we've got a kind of cylinder and a cone on top of that. First thing I want to do is identify the axes. So I'm going to put that at the bottom. Make sure you label that in your diagram. Everything is going to be measured with respect to this point, and your answer is going to be with respect to this point. You need to break your piece down into different shapes. So a cone and a cylinder are both in my table, so I can use those as my shape 1 and shape 2. Once you have that, you're going to put together your table just like you did before, except here, again, we got one row for each shape. We're going to have a column for volume rather than area, and then we're going to x, y, and z coordinates for the centroid. So I need to find the x, y, and z coordinates of the centroid for shape 1, which is the piece up here at the top, and then the x, y, and z coordinates of the centroid of the cylinder on the bottom. That'd be x, y, and z down here. Once we have each of those pieces, we have 3 things to calculate. We've got an x coordinate for our overall centroid, a y coordinate for our overall centroid, and a z coordinate for our overall centroid. And the process is much the same, we just have 3 of them now. So it can be volume 1 times x bar 1 plus volume 2 times x bar 2 divided by the total volume. That gives you the overall x bar. Same thing for y bar and z bar, except it's volume times y or volume times z for those calculations. Moving on to the center of mass. So the center of mass calculation is very similar to what we just did with center of volume calculations, except we're going to be using mass, in place of a volume. So for this, same process, use the mass of each part. We may be calculated as density times volume if you just have a material. It might be weighing the individual pieces to figure out the mass that way. Also, when we have a cutout, this is the mass of the material removed. So this is going to be a little more complicated. Like if you've got a cylinder with you've got like a box with a cylindrical cutout, you would need the mass of the box to start with, and then you would need the mass of the material removed through the cutout. So that's why it can be a little more complicated. Other than that, we have the same process. So some shape. Here I've got different materials, top and bottom. Identify your axes, identify the pieces. So the cone is 1, the cylinder is 2 again. Create your table. So here you're going to have a column for mass, and an x bar, y bar, z bar. Assuming these have uniform density, just look these up with the centroid tables just like you did with the volumes. Once you have that, you're going to do the following formula. So it's going to be for x, the x coordinate of the overall center of mass of this body. It'd be mass 1 times x bar 1 plus mass 2 times x bar 2, and then divide that by the total mass of the object. Repeat for I, so mass times y bar over total mass, and then repeat for z, so mass times z bar over the total mass there. So with this, let's also talk about the distinction between these two. So these are very similar processes, but not identical. One is weighted by volume, so it's a weighted average by volume. One is a weighted average by mass. That is the primary difference. So if the composite body has a uniform density, usually because it's made of one material, if this is just a machined part, The centroid of the volume and the center of mass are going to be the exact same point. So you can really use these interchangeably. Where we run into differences is if we have a body that is made of pieces. So if this is some sort of assembly, part of it's metal, part of it's plastic, part of it is wood, those different materials are going to have different densities. That is going to cause a difference in the weighted average. And the centroid of the volume and the center of mass are going to be different points. They're going to be close to one another, but they are going to be different points because of those differences in density. So just keep that in mind when you're doing your calculations. All right, and that's all I've got for today's video lecture. Thank you for watching, and I hope to see you again.